This lecture goes through more practice in solving differential equations using the strategy of separation of variables. Again, you'll learn more complicated strategies for more complicated differential equations in later courses, but for now we deal with this most simplest type, which still has some applications which we will look at momentarily. The idea generally is to try to solve for y and solve in a differential equation, but occasionally it's more convenient to put it in a different form which is more familiar. So for instance, if we start with y prime is equal to 2x over y, you can write y prime as dy over dx equals 2x over y. So dy over dx, you would multiply dx and y, and you end up getting down to here. The integral of y dy is equal to the integral of 2x dx. When you integrate both sides, you have half y squared is equal to x squared plus c1. Notice I use the subscript here because we're going to multiply everything by 2, so these are different random constants. And then rather than solving for y and having plus or minus and radical, we write it as y squared minus 2x squared is equal to c, which you can then recognize as a family of hyperbolas. This is again using the Leibniz notation I mentioned as far as writing y prime as dy dx, and then you're able to separate variables more clearly. So if we have a very basic differential equation, that is that the rate of change of y with respect to t is proportional to y, this leads very easily to exponential growth and decay. Y is equal to c times e to the kt. The proof is down here. You simply write y prime as dy dx. You separate your variables. Integral of dy over y is ln y. Integral of k dt is kt plus c1. Exponentiate both sides. E to the kt plus c1 becomes e to the kt times e to the c1. E to the c1 we write as c. And so we see that this is your exponential growth equation or decay coming directly from your differential equation. Here we have rate of change of y is proportional to y, so here's the differential equation that goes with that statement, which we already know can be solved as y is equal to c times e to the kt. This example though isn't really calculus based though at this point, because we have two constants c and k we're trying to solve for. So we have 2 points 0, 2 and 2, 4. Using those 2 points down here, we can solve for our particular model for this situation. Y is 2 times e to the 0.3466t, and then finally we can plug in 3 to get our answer. Of course, we have half-life examples. These are approximate half-lives of different radioactive isotopes, and so once again we're going to assume these decay, the decay rate is proportional to the amount, so leading immediately to this as our solution to the differential equation. We know that there's an initial amount of 10 grams. How long will it take to decay to 1 gram? And so the initial amount of 10 grams, we know that we can solve for c and get 10. And then knowing that the half-life is 24,100 years, we know that after that amount of time goes by, you have half of what you started with. So you have half of the initial amount, 10, so you have 5. So now we can use this equation to solve for our decay constant k. And now we have a particular model. And finally, if you want to find out how long it takes to get down to 1 gram, we can plug in 1 for our y value and go back and solve this for t. Now, knowing that if you do 1 half-life, you get down to 5, 2 half-lives, you get to 2.5, 3 half-lives, you get to 1.25. So this should be a little bit more than 3 half-lives. If this is your half-life, it should be 75,000 years or more. So it's a good idea to try to check your work in a way. And you can see it's about 80,000 years, so that makes sense. Here again we'll use exponential growth decay. This time we have exponential growth. 100 fruit flies the second day of the experiment, 300 flies on the 4th day. How many original populations? So we again have 2 constants to solve for, c and k. So the calculus has already basically been done in coming up with this differential equation solution. So the solution to the equation. So this is the pre-calculus really application of it. We plug in the points 2, 100 and 4, 300 to solve for c and k to get our specific particular solution for this situation. And if you want to know how many flies are in the original population, once you have c and k, we get our c down here, we know that it ends up being about 33. Another example, we have this time sales which are declining exponentially, so we use our exponential model. This isn't really much different from what we've been doing. Again, we need 2 points, so we plug in our 2 points and we end up solving for our model, so I'm not going to spend more time on that. And then finally, one more application where the differential equation is at least a little bit different than the previous examples. Instead of using decay rate is proportional to the amount you have, we have the decay rate is proportional to the difference between some amount and the amount you have. So this is Newton's law of cooling. Basically, the farther away the temperature is from the ambient temperature, the faster it cools. Solving this equation, we again do separation of variables. And so separation of variables, integrate both sides, and we can once again get our, here's our general solution. We still have a c and a k. We have 2 points though where we can use again. We go from 100 degrees to 90 degrees in 10 minutes, so that implies that the initial amount was 100 degrees, so 0, 100, and then after 10 minutes it's 90 degrees, so 10, 90, and we want to find out the time it takes to get to 80, so we have to get c and k by plugging in the points 0, 100 and 10, 90 into this general solution. When we do that, we get the particular solution, which is right here, and then finally to get the time it takes to get to 80 degrees, we plug 80 in for y, which is our temperature, subtract, divide, natural log, and so forth, and it takes about 24 minutes, so it takes this much longer to go down 10 degrees. So the first 10 degree drop only took 10 minutes, the second 10 degree drop took longer because of course it's cooling more slowly as it goes on.